You have already learned that the equilibrium in a system having two or more phases is known as heterogeneous equilibrium. Heterogeneous equilibria often involve pure solids or liquids. The concentration of these solids or liquids remains constant and does not change. Hence, while writing the equilibrium expressions for heterogeneous equilibria involving a pure liquid or a pure solid, the concentrations of these substances are excluded. Consider the thermal decomposition of calcium carbonate in a closed vessel. Solid calcium carbonate decomposes on heating into solid calcium oxide and gaseous carbon dioxide. The equilibrium constant for this reaction can be written as Kc is equal to the product of the concentrations of calcium oxide and carbon dioxide divided by concentration of calcium carbonate. Since calcium carbonate and calcium oxide are solids, their concentrations remain constant, and hence their concentration terms in the expression for equilibrium constant can be ignored. Now, the modified equilibrium constant for the system becomes Kc' is equal to concentration of carbon dioxide, or Kp is equal to pressure of carbon dioxide. This expression clearly shows that at a particular temperature, irrespective of the masses of the two solids, calcium oxide and calcium carbonate, there is a constant concentration or pressure of carbon dioxide in equilibrium with calcium oxide and calcium carbonate. It has been found experimentally that the pressure of carbon dioxide in equilibrium with calcium oxide and calcium carbonate at 1073 Kelvin is equal to 2.5 into 10 raised to the power 4 Pascal. Hence, the equilibrium constant at 1073 Kelvin, which is equal to the pressure of carbon dioxide, is equal to 2.5 into 10 raised to the power 4 Pascal. Some characteristics of equilibrium constant are: the value of equilibrium constant is independent of the initial concentrations of the reactants and products. For example, the equilibrium constant for the reversible reaction of gaseous hydrogen and gaseous iodine in a sealed reaction vessel, irrespective of the initial concentrations at 731 Kelvin, is 46.4. The equilibrium constant for a particular reaction at a particular temperature is always constant and changes only with a change in temperature. For example, the equilibrium constant for the reaction of 1 mole of gaseous nitrogen and 3 moles of hydrogen combining reversibly to form 2 moles of gaseous ammonia at 298 Kelvin is 6.8 into 10 raised to the power 5. At 400 Kelvin, it is 41. And at 500 Kelvin, it is 3.6 into 10 raised to the power minus 2. The equilibrium constants of a forward reaction and its backward reaction are reciprocals of each other. For example, the equilibrium constant for the reversible reaction of gaseous hydrogen and gaseous iodine to form gaseous hydrogen iodide at 731 Kelvin is 46.4. The equilibrium constant for the reverse reaction of the decomposition of hydrogen iodide at the same temperature is the inverse of the equilibrium constant for the forward reaction of the formation of hydrogen iodide from hydrogen and iodine. This is equal to 1 by 46.4. If a chemical equation is multiplied by a certain factor, then its equilibrium constant must be raised to a power equal to that factor in order to obtain the equilibrium constant for the new reaction. For example, the reaction of nitric oxide and oxygen to form nitrogen dioxide may be written in two equivalent ways. The first way of writing it is 1 mole of gaseous nitric oxide and half a mole of gaseous oxygen combining reversibly to form 1 mole of gaseous nitrogen dioxide. The second way of writing it is 2 moles of gaseous nitric oxide and 1 mole of gaseous oxygen combining reversibly to form 2 moles of gaseous nitrogen dioxide. The equilibrium constant for the reaction of 1 mole of gaseous nitric oxide and half a mole of gaseous oxygen combining reversibly to form 1 mole of gaseous nitric oxide may be written as Kp is equal to concentration of nitrogen dioxide divided by the product of the concentrations of nitric oxide and oxygen raised to the power of half is equal to, say, X. The equilibrium constant for the reaction of 2 moles of gaseous nitric oxide and 1 mole of gaseous oxygen combining reversibly to form 2 moles of gaseous nitrogen dioxide may be written as Kp' is equal to concentration of nitrogen dioxide raised to the power of 2 divided by the product of the concentrations of nitric oxide raised to the power of 2 and concentration of oxygen is equal to Kp square, which is equal to X square. Thus, you can say that the equilibrium constant for the second reaction, Kp' is equal to the square of the equilibrium constant of the first reaction. Given in the table are the equilibrium constant at various temperatures for the gaseous reaction of sulfur dioxide and oxygen to form sulfur trioxide. Can we guess at what temperature the reaction almost goes to completion? Can we predict the direction of the reaction at the given temperature? Can we calculate the equilibrium concentrations for this reaction? Let us see if equilibrium constant helps us in answering these questions. The knowledge of equilibrium constant helps us in predicting the extent of a reaction, predicting the direction of a reaction, calculating the equilibrium concentrations. Let us discuss each application in detail to appreciate the importance of equilibrium constant in a reaction. Predicting the extent of a reaction. The magnitude of equilibrium constant provides a useful indication of the extent of a chemical reaction. You have seen that the equilibrium constant for a reversible reaction is equal to the product of the concentrations of the products raised to their respective stoichiometric coefficients divided by the product of the concentrations of the reactants raised to their respective stoichiometric coefficients. As the products appear in the numerator and the reactants in the denominator of the expression, you can see that the magnitude of equilibrium constant is directly proportional to the concentrations of the products and inversely proportional to the concentrations of the reactants. Hence, a large value of an equilibrium constant indicates a high proportion of products to reactants, and vice versa. The magnitude of equilibrium constant, Kc or Kp, indicates the extent to which a reaction will proceed. If the numerical value of equilibrium constant is greater than 10 raised to the power 3, it means that the reaction nearly proceeds to completion and that the equilibrium concentration of the products is large. For example, the equilibrium constant for the gaseous reaction between hydrogen and chlorine to form hydrogen chloride at 300 Kelvin has a very large value of 4 into 10 raised to the power 31. If the numerical value of equilibrium constant is less than 10 raised to the power minus 3, it means that the reaction rarely proceeds, and also that the equilibrium concentration of the reactants is large. For example, for the gaseous reaction of nitrogen and oxygen reacting to form nitric oxide at 298 Kelvin, the equilibrium constant has a small value of 4.8 into 10 to the power of minus 31. If the numerical value of equilibrium constant lies between 10 raised to the power minus 3 and 10 raised to the power 3, it means that appreciable concentrations of the reactants as well as the products are present. For example, the equilibrium constant for the gaseous reaction of hydrogen and iodine combining to form hydrogen iodide at 700 Kelvin has a value of 57. The dependence of the extent of a reaction on its equilibrium constant can be illustrated as shown here. Let us now look how equilibrium constant helps in predicting the direction of a reaction. This is done by comparing the reaction quotient QC with the equilibrium constant Kc. So, for predicting the direction of a reaction, you also need to have knowledge of the reaction quotient. Let us first learn what reaction quotient is. At any point in a reversible reaction, the ratio of the concentration of the products raised to their respective stoichiometric coefficients to that of the reactants raised to their respective stoichiometric coefficients is known as the reaction quotient. QC with for molar concentrations and QP with for partial pressures. The reaction quotient expression of a reaction has the same equation as the equilibrium constant expression for that reaction. However, it is important to note that the reaction quotient is calculated using the concentrations or pressures at a given point of time in the reaction, and not the equilibrium concentrations or pressures. For a general reaction of the type A moles of reactant A and B moles of reactant B, reacting to give C moles of reactant C and D moles of reactant D. The reaction quotient QC is expressed as the product of concentration of C raised to the power of C and concentration of D raised to the power of D divided by the product of concentrations of A raised to the power of A and concentration of B raised to the power of B. Remember that the concentrations of the reactants and the products expressed in the equation are current concentrations and not equilibrium concentrations. Let us now examine how reaction quotient and equilibrium constant help us in predicting the direction of a reaction. If the value of reaction quotient QC is greater than equilibrium constant Kc, it means that backward reaction takes place. In other words, the reaction proceeds in the direction of the reactants. If the value of reaction quotient QC is less than equilibrium constant Kc. It means that forward reaction takes place. That is, the reaction proceeds in the direction of the products. If the value of reaction quotient Qc is equal to equilibrium constant Kc, then it indicates that the reaction mixture is at equilibrium. Thus, we can predict the direction of a reaction with the help of its reaction quotient and equilibrium constant. For example, the equilibrium constant for the gaseous reaction of hydrogen with iodine to form hydrogen iodide at 731 Kelvin is 46.4. Suppose at a given time, the molar concentration of hydrogen is 0.2 m. That of iodine is 0.4 m, and that of hydrogen iodide is 0.8 m. The reaction quotient, Qc, at this stage of the reaction is equal to the concentration of hydrogen iodide raised to the power of 2 divided by the product of the concentrations of hydrogen and iodine. This is equal to 0.8 square divided by 0.2 into 0.4. The value of the reaction quotient comes out to be 8.0. As the value of the reaction quotient is smaller than the equilibrium constant, the reaction proceeds in the forward direction. It means that more of gaseous hydrogen and iodine react to form the product hydrogen iodide. Let us now look at how equilibrium constant helps in calculating equilibrium concentrations. For this, let's consider a problem. Mix 2 moles of hydrogen and 3 moles of iodine together in a 1 liter closed vessel. It attains equilibrium at 440 Kelvin. Calculate the composition of the mixture at equilibrium given that the value of Kc for the reaction at 440 Kelvin is 0.02. The first step in calculating equilibrium concentrations involves writing a balanced equation for the reaction, like this. The second step is to set up a table describing the initial concentration, change in concentration on going to equilibrium and equilibrium concentration. The second step can be easily remembered in the form of ICE chart, where I stands for the initial concentrations or pressures for each species in the reaction mixture. C represents the change in the concentrations or pressures for each species as the system moves towards equilibrium. E represents the equilibrium concentrations or pressures of each species when the system is in a state of equilibrium. In constructing the table, use X to show the change in concentrations of the species. Use the stoichiometry of the reaction to determine the concentrations of the other substances in terms of X. The ICE chart for the given problem is: the initial concentrations of hydrogen and iodine in the reaction mixture are 2 moles and 3 moles respectively, while it is 0 for hydrogen iodide as it is not present at the beginning of the reaction. Let X moles of hydrogen and X moles of iodine combine to give 2X moles of hydrogen iodide as shown in the balanced equation. At equilibrium, the concentrations of hydrogen, iodine and hydrogen iodide will be 2 minus x, 3 minus x, and 2x, respectively. In the third step, substitute the equilibrium concentrations in the equilibrium equation and solve for x. The equilibrium equation for the reaction is Kc is equal to concentration of hydrogen iodide raised to the power of 2 divided by the product of the concentrations of hydrogen and iodine. On substituting the equilibrium concentrations and the value of the equilibrium constant in the equation, we get 2x square divided by 2 minus x multiplied by 3 minus x is equal to 0.02. This is equal to 4x square divided by x square minus 5x plus 6. This can be written as 4x square divided by x square minus 5x plus 6 is equal to 2 divided by 100. On cross multiplying, we get 100 multiplied by 4x square is equal to 2 multiplied by x square minus 5x plus 6. On crossing off 100 with 2, we get 50 multiplied by 4x square is equal to x square minus 5x plus 6. This becomes equal to 200x square is equal to x square minus 5x plus 6. This equation can be written as 200x square minus x square minus 5x plus 6 is equal to 0. This becomes equal to 200x square minus x square plus 5x minus 6 is equal to 0. This is equal to 199x square plus 5x minus 6 is equal to 0. This is in the form of a quadratic equation. ax square plus bx plus c is equal to 0. In this equation, a is equal to 199, b is equal to 5, and c is equal to minus 6. In order to solve x, you must use the formula x is equal to minus b plus or minus square root of b square minus 4ac divided by 2a. On substituting the values of a, b and c in the quadratic equation, we get minus 5 plus or minus square root of 5 square minus 4 multiplied by 199 multiplied by minus 6 divided by 2 multiplied by 199. This can be written as minus 5 plus or minus square root of 25 plus 4,776 divided by 398. This can be further written as minus 5 plus or minus square root of 4,801 divided by 398. The square root of 4,801 is 69.28. Hence, the equation can be written as minus 5 plus or minus 69.28 divided by 398. This can be written in two forms. One form is x is equal to minus 5 plus 69.28 divided by 398, which is equal to 0.160. The other form is x is equal to minus 5 minus 69.28 divided by 398. This becomes equal to minus 74.28 divided by 398, which is equal to minus 0.186. As concentration cannot have a negative value, it is clear that the correct value of x is 0.160. The fourth step is to calculate the equilibrium concentrations from the value of X. The initial number of moles of hydrogen is 2. Hence, at equilibrium, the concentration of hydrogen will be 2 minus 0.160. This is equal to 1.84 moles per liter. In the case of iodine, the initial number of moles were 3, and hence, the equilibrium concentration would be 3 minus 0.160. This is equal to 2.84 moles per liter. And finally, the equilibrium concentration of hydrogen iodide will be equal to 2 multiplied by 0.160. This is equal to 0.32 moles per liter. Step 5. Check your results by substituting them in the equilibrium equation. On substituting the concentrations of hydrogen, iodine, and hydrogen iodide in the equilibrium equation, we get Kc is equal to 0.32 square divided by 1.84 multiplied by 2.84. On solving this, we get the value of the equilibrium constant as 0.02. This is the same as the given value. Hence, the equilibrium concentrations are correct.